Good afternoon, everybody. My name is Griff Parry. I lead business development for games in Europe at AWS. Welcome to the session. I hope you're going to enjoy it. I'm going to provide a few words of context before handing over to David and Asko from Rovio, the stars of the show. I suspect that the majority of people in this room don't work in the games industry. So while many of you will know Angry Birds, which is an IP that's now extended far beyond games, including 2 major feature films, I suspect fewer of you know the story of the company behind it, Rovio. David and Asko are going to tell that story, and then they're going to describe their usage of the cloud to deliver agility and create competitive advantage. And then they're going to dive deep into their applications of ML and AI, which are notable in their range and ambition. This is about the games industry, but what you'll find is this business of fun actually involves some really serious applications of technology. If you are from outside the games industry, I'd expect you to find some real sort of learnings and inspiration in the hour or so that will follow. And we're really lucky to have David and Asko here with us to share their insights and experience. They're both experts in their field, technical leaders that solve business challenges with real creativity and vision, and they're both certainly worth paying close attention to. So without further ado, I will hand over to David.
Hi, good afternoon. So thank you for joining us, and with my colleague Asko, who will join the stage in a little while, we're going to take you through our journey with cloud services. We are cloud native as a company and have been running on the cloud for over 8 years. And I'm going to explain a little bit about how and what we've built. So personally, I feel actually really excited about working in games and this industry. It's a really mix of creativity and technology. But it's also the only place where I've been for an interview where when I come back, my kids ask me which Angry Bird I met. So we're going to focus on Rovio's tech and how we create unfair advantages we see it with the technology that we build. But hopefully, from today, you will see learnings, whatever industry you're in. So I'll just walk you through the agenda for the session. So we're going to talk a little bit about Rovio, and actually, we have a big celebration coming next week as well, which I'll come back to in a minute. I'll talk about our beacon, which is what we call our cloud services for our game teams. We'll talk about our machine learning story, and Asko then will join and go through a particular case we've worked on this year with one of our latest hit games, Angry Birds Dream Blast. And then I'll come back on and give you a few takeaways, hopefully that will be useful. And yeah, basically what we're trying to convey here is that our approach enables our core of our organization focus on creativity. And we want to bring games to market faster. We want to build games with more depth and more content, and also make them more personal for you as well, so a personal gaming experience. So we're celebrating our 10th birthday next week on Wednesday. So it's 10 years since Angry Birds was in the App Store. I think it was very much the start of the app economy, and obviously we're very well known for that game. It was actually, though, our 52nd mobile game, but really it was the starting point of the app economy and gaming that we have today on mobile. And I'm going to show you a video now of part of our celebration and what we're doing, just to have some fun.
Bring the anger! You're angry. We're angry. Everybody's angry. Introducing the Rage Rider. To celebrate Angry Birds' 10th anniversary, we created the first scooter powered by anger. Here's how it works. Just yell or scream about whatever makes you angry, and the Rage Rider turns it into power! Traffic jams? Power! No vegan options? Power! Narrators that can't control the volume of their voice? Power! The louder you yell, the faster it goes! The Rage Rider! By Angry Birds. Limited edition, not for sale. We only made 100 and given them to people that probably aren't you. Does that make you angry? Good, because it exists to show anger can be turned to something useful. Rage not included. Bring the anger!
And there's a few more things in the campaign as well, so please go online and have a look. But actually, there's for our brand, bringing the anger is about, showing how anger can be converted into positive action. And actually, as part of this campaign, we've teamed up with UNICEF. And in Angry Birds 2, one of our other lead games, you can play the game, and as part of that, the challenges, people completing challenges in the game, will lead to a donation to UNICEF, to Education and Emergencies Fund. So that's, so we want to be more than just fun. We want to also have purpose with our brand as well. So coming back to a little bit about Rovio before we move into the tech. So many of you have seen, Angry Birds plushies or t-shirts or the Angry Birds movies. Your kids may have been, we actually had our second movie this year. But actually 89% of our revenue comes from games. And we are about 400 people, of which 330 work in games. And there's actually 40 nationalities. We're based predominantly in Helsinki and in Stockholm. And I think and we have 9 new games in development that are being soft launched or tested at the moment and beyond what's already in the market. And we're building different genres of games with that as well. So casual games, RPG, 4X strategy games. That means that we're learning and becoming masters of different genres as well, and that shapes the technology that we need as well. The game server environment is different for a casual game versus a real-time PvP game, for example. So I'm going to show you Angry Birds Dream Blast. And briefly, hopefully this is a live demo, so hopefully this works well. And that will then set the stage for showing you some of the tech that's running behind this as well. Just give me a second, I will switch to my call. So that worked. And so this game is downloadable from the app stores. And you'll see here. So this is Angry Birds Dream Blast. And I will show you the core mechanics of the game. So this is a tapped clear match game, but with a unique physics part to this, gravitational physics, as you'll see. So as I pop and explode. Okay, so please download the game. I'm not going to spend a huge amount of time showing you the game, but I will come out of this. I don't want to retry, so and I will turn the sound off as well. So now I'll show you some of the tech and services that we're running behind this as well. So actually, the first thing you see here is a cross promotion or an ad for another game, for actually Angry Birds 2, which I mentioned, and you can click and install from here. This is run from our ads platform. Within here, you can see within the game, we are running live events within this game. So there's a Reds challenge going live. And you'll see in a little bit how we manage a calendar of live operations. Then you'll see there are chat and teams, and these things are being run from a game server. So there's leaderboards behind the live events, there's chat, there's teams, etc. And then, as it's a free-to-play game, there's also payments as well, and we validate the payments and have virtual goods behind them. So I think it gives you a brief intro to the game. And actually, if you go to the 4th floor in this building, there's a couple of stands that you can play the game as well. So let me switch back to the presentation. So the first live demo worked, second one to come. So cool. So then, what are we running behind this to make this run? So actually, let me start with talking a little bit about where we come from in 10 years. So 10 years ago, we didn't have our analytics. We were using a service called Flurry, and we were getting the data 24 hours later. Today, thankfully, we see stuff in real time, so we can act. We did have our own game engine. Today, we're predominantly using Unity. But there were no game servers, there was no ads, and there was no free-to-play mechanics in those days either. But our cloud story started 8 years ago when we realized that we needed infrastructure to manage payments and identity of our players, to develop centrally socialized gaming experiences like leaderboards, enable ads and cross-promotion in our games to monetize but also promote, because we were building a portfolio of games, and then solid analytics and tooling for that as well. So 8 years ago, Rovio set up on that journey, and today we call these services Beacon. And this is the place where all of our teams go, the game teams, user acquisition, ads, BI, and use this. And we have 4 principles that guide what we build and where we partner, and how we build. So we put our players at the center of everything we do, and you'll see in a little while how that then drives actions. But it means that actually we think about how we can maximize the fun of our players in the games first. Then we have always a single truth of data, so that we can drive decisions and automate actions. Then we look to enable game teams to focus on the game, either by sharing knowledge or then building services and capabilities of the game team so they can focus on just coding the game. And then we want to own our future as well. We see technology as fundamental to our business as we go forward. And we chose 8 years ago to build on AWS, and we're still running on AWS. So today, to give you some idea of numbers, we have over 1 billion player accounts. We serve tens of thousands of requests per second. We capture about 2 to 4 billion analytic events a day, about 1 terabyte of data. And we run on over 1,300 instances on AWS. And this is for our analytics, our services, and our game servers. And then we seek to productize to make it easy. So we build services and capabilities and productize those so our game teams can plug and play is the approach. So we're wrapping things in a dashboard that I'll show you in a minute, but then also providing them an SDK with common services and also third parties like ad network, user acquisition, attribution, etc. And also providing REST APIs. And then we're delivering those key services and running them 24/7 and providing, doing the manning so that the game teams don't get working at night. They don't take the first call. We have a team that takes that pain. And then in our services, we've got quite a broad set of capabilities from player identity, analytics, personalization, through to, build, but also providing privacy as a service, GDPR, CCPA, so the game teams can take our service and they don't need to worry about how, they just worry about the game again and not about implementing GDPR. We help manage that pain and also at the same time enable the privacy of our players as well. So let me switch back and hopefully the second live demo works. So as I showed a screenshot earlier on, this is actually now live, and it's a production version, so I will be careful with some of the things I do because it will change things live in the games, and I have too much authority. So this is the dashboard where our game teams come to. And most people in our company start here every day because what they do is they go and look at yesterday. They go and look at the revenue, the retention, they look at the A/B tests they've been running, and then they start their day, and they start configuring the game or experimenting, and they go from there. And so with Angry Birds Dream Blast, let me show you how they then use this. So I will. So this is an example of the analytics that our game teams run, and you can see that they've created some standard charts and then custom charts. We use a technology called Redash for SQL queries and Druid for pivot tables in here, and then HighChart is the framework. So we're not using a third-party visualization tool. We've embedded things in our own dashboard. This example is the time spent and session length in the game, and obviously you can filter this down. I'll then show you a couple of more services so you can see. So this is what we call the managed service. It's a segmentation and targeting rules engine for the game, so they build configuration. So if I walk, so you build a configuration of A/B tests or offers or events and build segments in there. And then what we pass to the game client, to the player, is when they join the game or when the game asks, we provide a flattened JSON configuration to the game of the configuration for that individual player. And I'll give you an example of, this is an A/B test that the game team was running last week around Black Friday, and they had a control and variance, and within that, actually some children as well, depending on your segment. For example, the GDPR one is because we enable players to opt out of personal offers, so anybody who opted out doesn't receive an offer, for example. And you can see within here, we can build criteria and configuration, and I can actually add one to this. And we can actually also use machine learning models in here as well. So, for example, we've got churn score, and we've also got spender prediction, and LTV in here as well, and we can use those models and apply them in the configuration here. And then and one more service. This is the last service I'll show you, but this is the live ops calendars that are running the events that are scheduled, and basically building a whole series of a timeline of events that are running, and you can see there are seasonal events. There was a harvest event, and then there are daily challenges, etc. within here. Basically, the game team can build these events in their game and then use this to manage the configuration of those events. So behind each one of these, there's a JSON configuration, again, with a template that doesn't require a developer. They can change the challenge and the content and the imagery, just by going into this tool, and then copy these and repeat them as well. And then one last thing in here I'll show you is actually to prove it's live, I'll press search and so this is my player profile in Angry Birds Dream Blast. And you can see here, we can get to the player level of understanding your state in the game. So it tells, for example, what level I'm on in this game, 975. It also has a churn score estimation for me. So, and my eyesight is not so good here, so nearly 0.3. A 1 is likely to churn, a 0 is likely not to churn. So I'm a regular player. I haven't played as much over the last 2 weeks, so probably my score has increased as well. But we can see in here, for example, even the rules that you match, etc. as well, so we can really get to the player level understanding. Cool. I will switch back from the live demo. Cool. So, going to talk a little bit about some of the things that enable us under the hood. And, the core of everything we do is analytics and our analytics pipeline. And some very clever gentlemen in the room who built this stuff as well, if you want to talk more about this. But fundamentally, this is foundational for us. This is how we know our players, how we make decisions, how we drive actions, including machine learning. So we're capturing events from the game client, we're collecting from the game service, and also third-party services like user attribution and ads. And obviously, to give you a view, user attribution in a mobile gaming context, it drives the way that we grow our business now. It's no longer about going to the App Store. It's more about bought media and performance marketing. And so this is real time. And then we have two parts of our pipeline. We have a real-time stream using Flink, and then we have an ETL process. And there, we're actually capable of running things on an hourly batch as well. And then for the game server side, we're so with Angry Birds Dream Blast, we're using what we've built, which is a reusable templates capability. Many of our early games with game servers were actually running on Google App Engine, but 6 years ago, and that was 6 years ago, but we've moved heavily towards AWS, mainly because of the capability of the cloud infrastructure you can get from AWS, but also the cost as well. So we also had more complex needs as we've done different kinds of games, for example, real-time player, PvP. But what we're trying to do here is very much deliver the game team something where they can focus on coding the game, developing the actual game, and not the infrastructure. So the purpose of the templates is within a few hours, actually, they can deploy a dev stage production environment, and they can choose from the templates what they require, what databases they require, and then also whether they're using containers or just auto-scaling of ECS. EC2s, and then other things like Jenkins out of the box as well. But we've gone further as well. So in Dream Blast, Angry Birds Dream Blast's case, that's enabled the game team to actually code there, but actually we have 2 games in soft launch that have the core of the same code for those games as well. So we've been able to actually shift projects and repurpose a lot of the code that we've developed. And we've gone further with that as well, of actually starting to build microservices as well. So we're starting to productize things that the game teams are doing and working with the game teams. So this is one example where we built a microservice for in-game messaging and chat and push notifications. And obviously, again, the fundamental point of this is we want things to be reusable where we can and where it makes sense, because what we're looking to do is get games to market. And with games like Angry Birds Dream Blast, that game's time to market was 9 months. So production to soft launch, to actually running the game and understanding, and improving the game and the ability to do user acquisition to global launch, all in 9 months, very compacted because we were able to reuse a lot of the capabilities we had. So I've gone through our cloud services, because I'm going to talk now about our machine learning story and where we've gone to and what we see the potential. And then Asko will join a particular case. So we see machine learning and AI is applying across the game development cycle, from game idea, all the way through distribution and marketing and monetization. And you can see, we see many different types of use case along this journey. So it can be from understanding the fun in the game, actually understanding if players enjoy the levels they're playing, to optimizing the pricing, or then creating content with machine learning, or predicting where we have problems and anomalies with our services. There are many use cases for machine learning. So we've adopted and been working on this in a journey. And our goal is to build games for you, so personalized games. And we started back in 2011 very much with collecting data and being able to do things at a macro level. So being able to run A/B tests and, effectively an A/B test, sets different segments, and then you apply a configuration to that, and you decide which is the best configuration. You make the choice, but that's a global thing. You end the day applying, and you apply the configuration globally to your game. Then we've moved on to working at a micro level. So, for example, measuring churn and then being able to act on churn. And, for example, we use churn score to improve the level funnel in one of our games, or we then use it to cross-promote our games to other games, to our players that we know are towards the end of the life cycle in the game. Then we're also using it to also optimize the levels in our game, or using bots. So we started that with a heuristic bot with Angry Match. But we've moved on, as Asko will talk to you, about using ML for level balancing in Angry Dream Blast. But we're also doing things like LTV predictions, anomaly detection. We're also predicting now the likelihood of spend in the very first session a player plays in the game as well. And obviously, many of our games don't convert in the first week. So we're actually making that prediction based on where that player is coming from and other factors. So let me invite Asko on the stage, and he will take you through the case that we have here.
All right. Good afternoon, everyone, on my behalf as well. My name is Asko Relas, and I work in our data engineering team, where we own our analytics pipeline that David showed you, but we also own the machine learning services and capabilities that we provide to our games through our platform, such as the churn prediction and other things that David mentioned. So last year, my colleague Vesa Siivola gave a talk on how we do player churn prediction, player lifetime value prediction, and such. So if you're interested in that kind of stuff, do check out our talk from last year. You'll find it in the AWS YouTube channel. If you search for AWS Rovio, it should be fairly high up on your list. But this year we wanted to bring something a bit different to the table. So I'll be talking about how we use reinforcement learning to predict the difficulty of levels in Dream Blast, one of our newer puzzle games. So the first question, of course, is why do you even want to predict the difficulty of levels? Well, we know that designing the level funnel of a puzzle game is something of a balancing act, because if those levels are too hard, it's going to give the players a feeling of you got to pay to win. They get frustrated, they leave one-star reviews, and they ultimately churn. Then again, if the levels are too easy, it'll make the game boring, and they'll churn because of that. So striking the optimal balance in terms of difficulty requires a lot of repetitive testing from our level designers who need to play their levels over and over and over again to get a feel for how difficult they are before actually releasing them. So if we're able to predict the difficulty of those levels already during their development, it's going to give us, most importantly, the ability to provide more consistent experience to our players that are, at the end of the game, they're waiting for new levels to be released, and we want to make sure that those levels are of equal quality to all the others. And it'll, of course, also allow us to spend a bit less time on that manual testing. So in order to be able to predict something, first you, of course, need to be able to measure it. And we measure difficulty through a metric that we call the pass rate, which is basically for a given level, the total number of times that it has been passed divided by the total number of times that it has been attempted. And that'll give you a number between 0 and 1 that will describe that level's difficulty. The overall concept of this project is fairly simple. We have a level designer who's working on new levels, a pack of levels. It's 10 levels in a pack. And when they feel that they're more or less done with those levels, they'll submit that pack for evaluation, where the bot will pick it up. It's going to start playing those levels, and it's going to record a number of statistics on how hard it thinks those levels are from its point of view. And then ultimately, we try to predict the pass rates of real players based on those statistics that we get from the bots. And here's what it looks like from the point of view of the end user, the level designer. So you're working on in your Unity editor, and when you feel that you're done with your levels, you're gonna press a button which will submit that level pack for evaluation. And once the evaluation is done, you're gonna get a Slack notification saying that your level pack has been evaluated. You follow that link, it'll take you to Beacon for the dashboards that will, among other things, show you how hard we think those levels will be. And we want all of this processing to happen at the least overnight. So that gives us some leeway in terms of what kinds of techniques we can use. What happens behind the scenes between submitting the pack from the Unity editor to receiving that Slack notification is something like this. So we HTTP post the contents of that level pack from the Unity editor to our API gateway, backed by a Lambda, which will store the levels in S3, after which it will start the execution of those bots. They're gonna pull the levels that they need, along with some predictive models from S3. And once the execution is done, they'll apply the predictions, store it in RDS, from which they can be accessed through our Beacon dashboards, and then the Slack notification goes out. So much of this is completely standard boilerplate stuff. So I'm going to actually, for much of this talk, be focusing on that box in the center that says bots, because that's maybe the only non-trivial part of this solution. So we need a bot, and there's a whole bunch of different approaches you can take to build one, starting with the simplest one to get started with the heuristic approach. You could also call it the rule-based approach, if you will, where the idea is that given a game state, you look at all the available actions that you have, score them based on some predefined rules, and you play the action that gets the highest score. The downside here is that you have only like one set of rules, one policy, if you will, for the whole game, and you could quite easily argue that if you have 2,000 levels, that one set of rules is not going to be optimal, if even good, for many of those levels. Another approach you could take is the tree search approach, where the idea is to build a tree of game states and transitions between those states via actions in order to be able to search that tree for the optimal path that will let you beat that level. And one such algorithm is, for instance, the Monte Carlo tree search, MCTS. And the definite upside here is that you need no understanding of the underlying game mechanics. You just need to know which actions are available at each state, and you'll be able to construct that tree from that information alone. So if you implement that for one game, you get plenty of code reuse for other games as well. But the downside here is that these methods tend to be quite slow and computationally heavy. So I'm fairly confident that this would not finish overnight. So we're actually going to strike this off the list. The third approach you could take is imitation learning, where the idea is that you collect data on how people actually play the game, and then you train a bot to imitate those people. You could argue that this would yield the most human-like bot, since you are actually learning from people. But again, one of the downsides is that you have one policy for the whole game, plus you're going to need to have a bit more instrumentation in your game, because you need to be able to collect those each game state and the action that the player took in that state, and send that server side to serve as training material for the machine learning process. And since we wanted to keep this project as inobtrusive as possible, we're actually going to strike this off the list as well. Ultimately, or finally, we got reinforcement learning, where the idea is that the bot will learn how to play through experimenting by its own. And the upside here is that you can learn a different policy for each level, meaning that whatever novel designs your level designer maybe throw at the bot, it'll be able to adapt to those new level designs, because it learns every level individually. And I would personally argue that this is actually the reason why this approach is the most human-like, the ability to adapt to novel situations. Downsides here are that it's definitely slower than imitation learning, but still can be made faster than the tree search approach. So with reinforcement learning, the idea is that you have an agent, the bot, that will interact with its environment, the game. And it's going to start off by not knowing the first thing about how to play that game. It's just going to try random actions in different kinds of game states. And it is then the responsibility of the environment to provide feedback on which actions were positive, which ones took it towards actually completing that level, and which actions were negative, just wasted moves. And so the bot starts playing, and it starts playing terribly. And that is the whole point, because it'll learn from its mistakes. And after some 3,000 rounds of practice, we observe that it is actually getting quite good. So here's what that looks like. Before playing the video, here's what you're going to see. On the left, we have the game. And on the right, we have basically what the bot sees or how it evaluates this particular state in the game. The more yellow, the more valuable. So clearly, in this state, it wants to play that action, which corresponds to popping that particular blue bubble over there. And on this level, at this stage, your goal is to clear those pink bubbles so you can open that pink lock, and that'll take you to the next screen and onwards. So here's what that looks like. So puts a booster in there, another one up there. They get merged. And definitely wants to play that booster now. Let's look into pick those 3 pink ones off the table. Puts a small red booster over there, pops that up, and the lock is opened. And now we need to clear those orange jellies to move forward. So puts a single booster in there and is able to clear all of them. And now what we need to do is break that rock in order to release those chains. Puts a booster right on top of it and blows that up. And now all we need to do is clear those black nightmare clouds and the orange jellies that are left. And manage to do that with, again, a single booster. Ultimately clearing the level with 11 moves left, and I gotta admit, the first time I tried this level, I didn't even clear it. So if nothing else, the bot is already a lot better than I am. For those of you who are know reinforcement learning a bit more, our particular approach is our own adaptation of the famous deep Q learning algorithm. And so since we have actually access to the game's source code, we don't necessarily need to use raw graphics as input for the learning process, but instead we can extract a more dense and more meaningful numeric game state representation from the game and use that as input. And since we're not using graphics, we don't necessarily need to use convolutional neural nets. We can use a simple feed-forward architecture instead. And the particular flavor of Q-learning that we use is the dueling double Q-learning with a prioritized experience replay. We use PyTorch as our framework. And at this point, we often get a question like, why PyTorch? Why not TensorFlow? And so when we started the project, we felt that we're going to be more productive with PyTorch. But given the recent release of TensorFlow 2.0, the argument for developer friendliness is definitely getting a bit thinner. So if you're going to do something like this yourself, I would just suggest that. Go with whatever framework you feel more comfortable, more productive with, and you'll definitely be able to implement whatever you want in either one of them. All right, so now that we have a bot that, if nothing else, plays better than me, so what we're going to then do is we're going to have it play many, if not all, of the levels that we have out there currently. Because for those levels, we actually know the player's pass rates, and that is the thing that we're trying to predict. So we also need to collect some corresponding data from the bot that will describe the level's difficulty from its point of view. So it starts practicing on level 1, practices for 3,000 rounds, after which we stop the learning process, and we're going to have it play 1,000 rounds more. And during those 1,000 rounds, we're going to observe how many times it was able to clear that level, what percentage of that level's goals it was able to clear on average, how many moves it had left on average at the end of the level, and if it fails to beat that level, we give it a cheat mode where it gets extra moves until it actually does clear that level, and we observe how many of those it needed on average. So do that for level 1, for level 2, level 3, all the way to level 1,000 or so, depending on how many levels you have out there. And all of that takes, of course, quite a lot of time. Because, like I said, in order to get accurate enough statistics that don't fluctuate too much, After practicing for 3,000 rounds, it still plays 1,000 rounds more. So that's 4,000 rounds of gameplay for a single level. And if you have 1,000 rounds, 1,000 levels, that's effectively roughly 4 million, or exactly 4 million rounds of gameplay. And one round can take anywhere between 5 to 10, even 15 seconds, even with sped up physics. So that's quite a lot of time. If you were to collect the data in such a strict sequential manner, it would take over a year, or actually with the number of levels that we currently have out there, that number is closer to 5 years. So that's a bit unfeasible, to say the least. And this is where AWS really helps us with this particular use case. So what we do is we bundle the game binary and the bot source code to a Docker container. We run one container per each level using AWS Batch. And that takes the data collection time down from a year or even 5 years to just 2 days for any number of levels. And there's a catch there. For any number of levels, that also means a single level. So this is not going to be good enough for our overnight execution requirements. We need to do a bit better still. And so what we do is we actually, within that container, we launch multiple parallel instances of the game and the bots and learn from several parallel bots running at the same time, which brings the data collection time down to just 4 hours for any number of levels. And that's a bit more feasible than 5 years. So here's what goes into that container. Starting from the basic building block, we have the agent, the bot, and the game that it interfaces with, and you're going to have several of those in parallel. And they're going to start exploring, playing the game, collecting experience, and we feed that into a buffer as effectively just a simple DQ data structure so that older experience is forgotten, newer one is retained. Then you have a separate learner that will pull experience from that buffer. It's going to learn how to play the game better, and it's going to propagate those better neural net models to those agents, and this loop goes on for 3,000 rounds. And those two are a separate Python process, put everything into a container, and we run these on C5 instances. At this point, people often ask, why C5? Why aren't you using GPU-enabled instances? Because you're doing kind of deep learning anyways. Why not GPUs? The short answer is because we don't need to. We can get an 8-fold parallelism with a single C5 2x large, and that's good enough to take it down to just 4 hours. If we wanted to go further and parallelize a bit more to take that 4 hours down still, we could increase the number of agents, but that learner would become the bottleneck. So you could scale further by using a GPU-enabled instance such as a P3 8x large, with which you could maybe expect to get something like a 30-fold parallelism, bring that 4 hours down to just 1 maybe. If you wanted to go even further, you'd scale across multiple machines. Maybe you'd take that buffer out and replace it with a document DB. You could have an arbitrary amount of agents feeding experience into that document DB, and you'd have a separate GPU-enabled process pulling that experience from that document DB. But we haven't needed to go that far yet. All right, so now that we have data from a large number of levels, both in terms of how hard it is for the bot, and we know how hard they are for people, so we just join those two together, feed them through a machine learning algorithm, which will learn a regression model that allows you to map from those bot statistics to the expected player pass rate. Then when you get a new level that hasn't been released yet, collect the same 4 metrics, feed them through that model, and it'll give you a prediction on how hard those levels are. For regression modeling, the statistics that we collect from the bot and the features that we use are the pass rate, how many moves it had left, the level objectives cleared, the extra moves given, and for the last 3, we also calculate means and different percentiles. We use scikit-learn as our machine learning toolkit, and we observe that we get the best prediction accuracy using the extreme gradient boosting algorithm. No big surprise there, really. But one thing that you need to be mindful of is that these tree-based algorithms, such as XGBoost, can't really extrapolate outside the range of data that you've provided them during the training process. And so, since currently, and we intend to keep it so, we don't have any impossible levels in the game, So we don't have any training data on what impossible levels look like. And so what we need to do instead, is to have an additional kind of like pre-classification step between flagging those impossible levels and filtering them out before actually trying to kind of like predict accuracy. Another question that we typically get is how accurate is it? Here's what it looks like for one individual level pack. The yellow line is the ground truth, and the pink one is the prediction. Sometimes it's quite spot on, sometimes it's a little bit off, sometimes it's a bit more off than what is shown here. But throughout our validation data set, we observe a mean absolute error of 0.15, of which I am quite proud because looking at the published literature around this topic, this is actually better than anything that we've seen out there. So quite proud of the work that we did with the team. But we don't want to stop there, because if you think about these casual, free-to-play puzzle games from more of a business point of view, you could consider it to be something like a triangle like this, where if you move one corner of that triangle, the other two will move as well. If you make a level harder, more people are going to churn playing that level, but the ones that are left behind or are still playing will on average generate a bit more revenue. So the question is that, can we actually then, if we can predict difficulty, could we derive the churn and revenue predictions as well? Let's look at the data. So here's what churn looks as a function of difficulty. So each dot here is one individual level. The color of the dot signifies how far along in the game that level is. So the lighter the bubble, the earlier in the game it is, the darker it is, the further in the game it is. And on the x-axis, we have the difficulty, the pass rate, easier levels to the right, harder levels to the left. And on the y-axis, we have the churn rate of that level. So what you can see here is you could easily imagine the kind of like the curve for level 300 being something like that. For level 800, maybe something like that. So basically the same curve, but just a bit steeper. And intuitively, that makes sense, because the further along in the game your players are, the more engaged they are, and they're less likely to churn even when you throw a bit harder levels at them. And this is really great, because now all you need to do is think about what kind of a function would yield that kind of a relation, and that's definitely something like a negative power function. So what you do is you take that and plug it into some function fitting algorithm like gradient descent, and you'll get a function with which you can map your pass rates into your churn rates. If you look at revenue, we observe a similar but somewhat inverted relationship, where the further along the players in the game, the more likely they are to spend money on harder levels. And again, that is intuitively quite sensible, because the people who make it to the end of the game within the time that it's been out are probably more likely to have spent money in those harder levels where others may get stuck. So in summary, AWS Batch is great for these embarrassingly parallel workloads, such as having a bot play 1,000 levels concurrently. Doesn't get much more embarrassingly parallel than that. And all in all, parallelization is really key to implementing fast enough reinforcement learning for business use, bringing down the time that you need from days or weeks to just hours. And you could, of course, speculate that if you have the ability to predict difficulty, churn, and revenue of levels, the logical next step might be to try out procedural content generation. With that, I'll hand back over to David for closing remarks.
Thank you. Yeah, thank you, Asko. I think with that case, actually, it's helped us improve the experience for our really engaged players, because what we historically did was push levels out and then tune them based on the feedback we got on how playable they were running A/B tests. Today, we can actually do that before we ship the levels. So I'll give you some takeaways, and then we'll open up for questions. So today we've taken you through how we build on the cloud and then how we've evolved to use machine learning. And I think some fundamental things for you to think about. For us, we talk about players, not users, but we put the player at the center of everything we do. And that means that we build player profiles and we understand what's going on with each of our individual players and then drive actions around those player profiles. For us, analytics is fundamental. We have one truth, we have one data lake, and that then empowers us to do the clever things that we're doing on top of that. Then our approach, as you've seen, we've set out a vision of where we want to go with machine learning, but with our services, we want to bring really personal gaming experiences to all our players. And we'll do that through experimenting. So everything we do, we experiment, we run proofs of concept, then we learn from those, we iterate, and we productize, so then we can leverage that across all of the games. We have 20 active games at any given moment. So then we can leverage all the game teams that we're developing can leverage those services and those capabilities. And then we see that machine learning will change the game, excuse the pun. But for us, this personal gaming experience will come from being able to understand our players better and actually provide them an experience that meets them as individuals. So, for example, we've talked about tuning levels here. Well, what about actually providing you levels to meet your skill capability, or helping within, say, an RPG game, which are more story-driven, to actually help you with the journey, the kind of play you want to play, rather than the journey that we give you. So, for example, if you like fighting or like healing, for example, those kind of things. So, and also teaching you as well, helping you to improve, using other players as the benchmark to understand how you can win in a battle, for example. So these kind of things will come through machine learning, and it will change the kind of games that we ship, and will make them more individual to you as our players. So I hope from this session you've got a good understanding of what we're doing, and we'll open up for questions. I think that Griff will join us on stage to help with that.
Yeah, thanks very much, David.
Yeah.
That was fantastic. We have a few minutes for questions. There is one microphone there, or if you're feeling loud, shout out your questions and I will repeat them. So who has questions? Anyone? Yes, you.
The bots that you're running, are those running in AWS, or is that somewhere? How close that?
So the question was, the bots that we have, are they running on AWS or?
Are they running community headless client in AWS?
Yeah, exactly. Yeah. So that's a headless build of the game, and yeah, it's running in those Docker containers, and we interface with the bot to that game because it's a Unity-based game. We have the Unity ML Agents API, the Python API that allows us to interface from our Python code into the game directly.
Next question.
Like the levels were deterministic, like they would be the same setup every time. Is that correct?
So the question was, are the levels deterministic? And the answer is no. There's a randomness to how things are, the different objects spawn. So it's different every time. And that's why you need those 1,000 rounds of play. Yeah.
Next question. Yeah. Speak at the microphone since you're close to it.
Is there a CNN mode before DQN mode?
I'm sorry, I didn't.
Is there CNN mode before DQN?
Sorry.
CNN.
CNN.
Yeah.
We did not, no, we don't use convolutional neural nets.
So you not use video input?
I'm sorry, I'm having a hard time hearing.
What's the input for training?
What's the input for training?
Yeah.
So it's kind of like a dense vector of numbers that we extract from the game. We don't use graphics. We have more of a more compact numeric representation that is more kind of extensible for the game state.
Okay.
Thank you.
Thank you.
Next question.
Hi, how do you prevent the model from learning unhuman characteristics and doing unhuman-like actions?
We've observed that there are kind of like some levels where people don't see something that the bot, which has basically, in its access to the game state, that where it actually typically outperforms people quite a lot. And we don't have a solution for that, but luckily those are few and far between.
So the follow-up to that is then, are you able to kind of correct that behavior when you spot it in action when running the tests?
Yeah, we can. It does take quite a lot of like tweaking of the reward function of that reinforcement learning process, but it's possible, yeah.
Thank you.
Any other questions? Going once? Going twice? Okay, listen, from me, thank you very much, David. Thank you very much, Asko. That was really insightful. Thank you very much.
Thank you.